Okay, we're back. So let's continue from where we left off. I failed to mention this at the beginning. So on my syllabus, I have that my office hours are 7:30 to 8:30 on Mondays and Wednesdays. Since there are only 5 recitations, whereas in a normal semester we would have 14-ish, I think it might be a good idea to have my office hours to be pure problem-solving sessions. So if they're completely optional, they're not worth any points, but I think it might be helpful for a lot of people who are struggling with the material to have some more examples. So that's what I'm going to do in office hours when class ends. Any questions before we resume? Okay, so this was a lot of theory, so let's actually do one example. So let's just make sure I'm all good here. Okay, I'm good. So let's have 2 DFAs. So let's have M1 be this DFA. 1, Q1, final, 0, 0, and let's put 1 on there. So we haven't really talked about this, but if I have a transition which has a comma-separated list, that means multiple transitions. So here it just means a transition on 0 to go back and also another transition on 1 to go back. So let's have that be M1. And I'm going to make this second DFA vertical, and you'll see a reason why in a second. So let's have it be 3 states. So R0 is my start state. R1, let's say it's final. And R2, I'll zoom out a little bit. So let's say 0, 1 here. 1 with a loop on 0. And then 0 back with a loop on 1. First check. Are these 2 things DFAs? Are you sure? They seem to have a transition on 0 and 1 on all states. But what's the alphabet? We have to specify the alphabet. It could be 0, 1, 2. In that case, these are not DFAs. So let's just make our lives easy and say the alphabet 0, 1. But it's always a good check to make sure. Well, we could pick either union, intersection, symmetric difference, or set minus. Let's make this easy, and let's do union first. And then we'll work in intersection in a bit. So what did the construction say to do? It said that we needed to make a state for all ordered pairs of states from the first machine and the second machine. So how many states will I make here? Yeah, 6, because I have 2 in the first one and 3 in the second. Hence the name product construction, product of the number of states. So I'm going to have a state Q0, R0, Q0, oh no, I'm going to do it this way. Q1, R0, and then Q0, R1, Q1, R1, and then Q0, R2, and then Q1, R2. And something that you should be thinking about as we're going along with the class, but in particular about this. Did we need in that construction some sort of intellect, or did we need to look at the DFAs and see their structure or anything? No. So this is a completely mechanical process. Something a computer can do. Okay? So that's just something to think about. Computers can solve this problem. Given 2 DFAs, produce the product DFA. What's the start state of this new DFA I'm going to make? Q0, R0, because it's the start state of the first, start state of the second. So that's my start state. We'll do final states at the end. So let's look at Q0, R0. How do I figure out where I go on the input 0? Look at the original DFAs. What did the first one do? It goes to 0, so Q0 is going to stay the same. And R0, where did I go? R1. So I'm going to go to Q0, R1. Good. Okay. Where did Q0, R0 go on input 1? Well, Q0 went to Q1. So I'm thinking Q1 right now. Where did R0 go? Also R1. So the state I go to is Q1, R1. Nice. 2 transitions done. How many more to go? 10. How do I know it's 10? Because I have 6 states and I need 2 transitions each. Cool. So let's do Q1, R0, the one in the upper right. So Q1 on 0, where do I go? To Q0, so I'm thinking left column now. R0, where did I go on input 0? R1. So the unfortunate thing about product construction is that things cross. Input 1, where do I go? Well, Q1 goes to Q0 always. So Q0. R0, where do I go on 1? R0? R1. So it's the same transition. Okay? So now let's go down to the second level. Q0, R1, where do I go on 0? Q0 is going to stay the same, and R1 is going to go to R1. So what is this transition going to be? A self loop, yeah, on that same state. Yeah, the worst part about state diagrams is that everything gets messy. Let's put it lightly. Q0, R1 on input 1, where do I go? Q1, so Q1, so I'm going to go to the right column. Where do I go on R1 on input 1? R2. So I'm going to come down there. And stop me if I make a mistake, because I've been known to make mistakes. All right, Q1, R1, where do I go on input 0? So it's always going to be Q0, because that's how the first machine's defined. Where do I go from R1 on 0? R1. So I'm going to come back straight across. Are tables better or state diagrams better? Tables. Thank you. So just letting you know before you get your problem set 1. Use the table. All right, so Q1, R1 on input 1. Q1 goes where? Q0 always. R1 goes where on 1? R2. So I'm going to make this easier and come around here. No one said lines have to be straight. Yeah, except geometry. All right. Q0, R2. Where do I go on input 0? Always Q0. R2 on 0 goes where? R0. So I'm going to come all the way back to the start state. See why formality is better? All right, Q0, R2 on input 1. I'm going to go to Q1, and R2 on 1 goes where? It goes to R2. So I'm going to go to state Q1, R2. Two more transitions. Q1, R2, where do I go on input 0? So I go to Q0 always. R2 on 0 goes where? R0. Oh boy. I've had recitations where it gets worse than this. Trust me. All right, one more to go, finally. Q1, R2 on input 1, where do I go? Q0 always, and R2 on 1 goes where? R2. So I'm going to go to Q0, R2. Did any of that have anything to do with union? No, had nothing to do with it. So if we're doing union here, so I'm going to make a note that this is union. Yeah, go ahead.
Not supposed to be one for Q1 R2. Q1 R2.
Which transition?
Q1 R2 to Q0 R2.
Okay, let's make sure. Q1 on 0 goes to Q0, so I'm in the left column. And R2 on 0 goes to, yeah. Oh, that should be a 1, sorry. Yeah, you're right. Thank you. Thank you. All right, so if I wanted to, so first off, what thing of this DFA have I missed? The set of final states. So how do I determine what thing's a final state and what isn't? For union, yeah. Okay, so I need to look at both coordinates in all states. Yeah, go ahead.
Do you still leave in the Q1 R0 state?
I'll talk about that in a bit. So I need to figure out what things are final and what things are not final. So Q0, R0, am I going to make that final? No. Q1, R0, should I make it final? What about that whole right column? Yes. See why I wrote the first DFA horizontally and the other one vertically? So I note when I do union, I can look and say, okay, yeah, the Q1 column is going to all be final. What do I know now for the M2 DFA? All the R1 states are going to be final, so this one's going to be final too. And that's the construction, product construction. So a great point was raised. Do I need that Q1 R0 state? No, why not? I can't reach it from the start state. So could I axe that state and not change the language? Yeah, I wouldn't change the language because I can't get to that state. But why should I keep it there? For completeness, and what's another reason? Did I look at the original DFAs and their structure? Well, I looked at individual transitions, but did I say, okay, I might not ever reach this particular pair? No. So this process is entirely algorithmic. It's defined exactly in terms of the original two DFAs. It'll always work. I don't know in general whether I could remove a particular state. Sometimes I might not be able to. In this case, I can, but I don't know that in advance. So if I do this completely algorithmically, I know it will work for sure. Okay? I don't need any sort of intelligence or brilliance to be able to produce this DFA. Okay? Any questions on this example?
So once it's finished, would you pull that out, or would you just leave it there?
So it depends. If the question asks for you to produce it in terms of the product construction, leave it in. But in terms of, like if you, for whatever reason, were producing DFAs for a company, and you wanted to be as efficient as possible, yes, remove it. And in fact, there's a question on the problem set that will be a bonus question, which will be about how can I minimize DFAs as much as possible? So it's a great question, though. Any other questions? All right. So we solved union in terms of regular languages being closed under them. What's the next one that we haven't done?
Intersection.
Well, we did intersection. What's the one we haven't done on the list of regular operations? Well, star's the third one. What's the second one? Concatenation. All right. So let's look at concatenation. And let's remind ourselves what it is. this is L1, L2 is W1, W2, such that W1's in L1, W2's in L2. So just the definition of concatenation of two regular languages, or two languages in general. So our question is, if L1 and L2 are regular, is L1, L2 regular? So maybe we can go along a similar strategy that we did before. So what we're presented is this string W1, W2, and I'm going to put some middle part in here, I minus 1, WI, WI plus 1, all the way to WN. And so our goal is to say, okay, some prefix of this string, let's just say this prefix, maybe, this belongs to L1, and then this suffix, the rest of the string, belongs to L2. And our goal is to produce a DFA such that we can figure out the first part, yeah, it belongs to L1, and then, yeah, the second part belongs to L2. But I think there's a problem here. What is the problem?
You have no idea what I is.
I have no idea where the split is. I have no idea. It's not presented to me on this input. There's no little marker to say, okay, yeah, it ended right here. And another thing, there might not even be a split. It might not even belong to the concatenation. How do I know? It seems pretty hard for DFAs to be able to do this. If only there was a way to guess, a way to say, okay, I, at this particular point, am going to guess that I'm done reading the first part of the string, and now I'm going to read the second part of the string. If only there was a way. What do you think we're going to do? We're going to define a way. So we're going to take a slight detour and talk about a generalization of DFAs such that we allow this type of guessing to happen. And so in whatever this model we're going to come up with, this guessing thing is going to make concatenation a lot simpler. And then eventually we're going to show that this model, this generalized model, is equivalent to DFAs. And that will be our proof that regular languages are closed under concatenation. All right. Any questions before we go into the cool stuff? All right. So these things are called nondeterministic. Finite automata. So in our model of DFAs, deterministic machines, what we had is that at every single point, we must execute a transition and read a character of the input. Maybe what we can do in our idea of trying to work with concatenation is, I'm going to guess that the second part of the string is going to start right now, but in order for that to happen, I need to execute a transition. Maybe I could have a transition where I don't read something along that transition. Okay? So we're going to allow that generalization. So the ideas here, we're going to have two things. We're going to have what are called epsilon transitions. So here, we're going to have no input character is read when executing it. Not executing it, traversing the transition. Okay, so I'm going to have the same, so I'm going to define it formally in a second. But the idea is that in addition to what we had before, we're going to allow you to have these so-called epsilon transitions where I don't read a character if I'm going to choose to execute that transition. Okay? I don't have to execute this transition because I have choices now. Okay? And, well, since I can possibly have choices, maybe what we can do is instead of having this total function thing where I have exactly one transition on a particular symbol defined, maybe I have multiple. Or maybe, could I have 0? Maybe? Sure, let's be as general as possible. So we're going to have multiple, or allow for multiple transitions, including 0, on the same symbol. So these are the two generalizations of deterministic machines that we're going to make for non-deterministic machines. And so you may be wondering, what does this non-deterministic actually mean? And so this is probably one of the most misused terms in all of this class, okay? So don't trust what people say on this. So some people say, and I've been in classes where people say, this is just basically unbounded parallelism, which means that if I have choices to make, let's say I have 2 choices on a particular symbol, I'm going to execute both of those transitions in parallel. That is not what's going to happen here. So the informal definition of choosing. The informal definition is, suppose that what this machine is going to have is something, maybe you would like to call it a crystal ball or some magical device. And what is going to happen is it's going to say, here are the transitions that if I were to take them, have some way of me to accept this string. So as an example, so if I have some state right here, and I have 2 transitions on the symbol A to different locations, and let's say that the first one, if I took that transition, there is a way for me to accept, and for the second, there's no way to accept at all, then this machine will choose that first transition, okay? But of course, it may be possible that that both transitions will lead to acceptance. And now the machine will have to choose which one is going to happen. So there's no predefined rules here. The notion of non-determinism is, if there is a way to accept, it will choose one of them, okay? It will choose one of those transitions, as long as there is some way for the string to be accepted by the machine. Okay, yeah? It'll still execute some transition. But if there was some transition, like over here, that there's no way to accept, so like all of these are non-accepting, it'll definitely not choose that transition. But if there happens to be, like all of these will eventually not accept, then we don't know what the machine will do. It'll just pick one. Okay? Any questions on what non-determinism actually means? Okay, so let's formally define an NFA. So an NFA is a something tuple, we'll get to in a sec. And you'd be surprised to see that it has the same 5 pieces. Not exactly the same, but it looks the same. So it is a 5 tuple. Q sigma delta Q0 F. Okay? Where Q is a finite set of states, exactly as before. Sigma, finite alphabet, exactly the same as before. I'm going to skip over the transition function. Q0 is a member of Q, is the start state. Exactly one start state as before. And F is a subset of Q. So those four pieces are exactly the same. Okay, so I'm going to have a set of states, some alphabet, some predefined start state, and a subset of the states being final, just like with DFAs, exactly the same. And so you may think, great, the transition function is going to be exactly the same too. And no, it's not. Because we need to incorporate both of these ideas into the transition function. So we have to remember, we need to allow for epsilon transitions where I don't read a particular symbol on that transition, and I need to account for having multiple transitions to different states, possibly. So let's define the transition function. So it's going to work exactly the same as before, where I'm going to, no, it's not going to work exactly the same as before. It's not going to work the same as before. But I'm going to pick one state, and now, instead of looking at a symbol in sigma, I could be looking at a symbol in sigma, or what? On a transition. Or epsilon. Okay, so now I need to express in the second coordinate picking something out of sigma or epsilon. So instead of Q cross sigma, it's going to be Q cross sigma union the empty string, or epsilon. So I have to put union here because the second coordinate, well, every argument of the function is always a set in this case. So I gotta wrap the empty string as a set and then allow it into the possible things I could put in the second coordinate. So this is just saying every transition is going to either have one symbol on it or be an epsilon transition. Okay? So that takes care of the epsilon transition part. So now, what do we got to do? We got to account for the multiple transitions part. Well, let's see. Could I have if I have a state with no transition on a particular symbol, or no transitions at all, could I have that? Yeah, I may have some state with no transitions coming out of it because I said I include 0 as the number of transitions on some symbol. So I may, on some state, go nowhere on any transition. Could I also, on some state, on some symbol, go to every state? Yeah, I'm saying that we could have multiple transitions on the same symbol. Could I go to some subset of the set of states as well? Yeah, I didn't say how many you had to have. I just said you can have some number. Oh, could I have any subset of the set of states? Possibly. That I can go to. Yeah, any subset. Oh, what is any subset of Q? Or the set of all subsets of Q? Power set of Q. Isn't this stuff so cool? Power set of Q. Okay? So let's work with an example. So let's incorporate multiple transitions and epsilon transitions in the same example. So Q0's start again, Q1's final, and Q2 is not either. So I'm going to have an epsilon transition here. Let's say the alphabet 0, 1. Okay, let's work with that example. So I have an epsilon transition from Q0 to Q1, And we incorporated multiple transitions on the same symbol with Q2 having 2 transitions on 0. And we also did it with Q1 because we have no transition coming out of it on the input 0. So if I happen to be somehow in Q1 reading a 0, then I'm stuck. I can't progress anymore because there's no transition defined for that. So let's see. So let's look at the input, I don't know, 1, 0. Keep it simple. So what state do I have to start in? Q0, always. Well, let's see. I could take the Q0 to Q1 epsilon transition without reading any input. Could I take the Q0 to Q2 transition? No, because that has a 0 on it. So, and we know that the first character is a 1, so we cannot take that Q0 to Q2 transition. So, I must go to Q1 without having read anything. So, here's another difference between unbounded parallelism and nondeterminism. I'm only ever in one state when the nondeterministic machine is executing. I'm not in multiple states at the same time. I'm in exactly one state at any given time. Okay? Well, I'm in Q1 now. So what is the only transition that I can do? I need to go from Q1 to Q2 because that's the only possible transition. I have no choice in this particular case. So I need to go to Q2. Well, I'm in Q2 now. Now I have a choice, right? I have a choice that I could either go back to Q1 reading a 0, or I can go to Q0 reading a 0. So will both opportunities or both choices allow me to eventually accept? Yeah, so if I happen to pick the Q2 to Q1 transition, I immediately will accept because the input is exhausted now. But if I happen to pick, let's say, Q2 to Q0, let's just say the machine happened to pick that one. Well, I haven't accepted yet, but I've ran out of input. Oh, but I can still take the epsilon transition without reading any more input. Even though the input's exhausted, I can still take epsilon transitions as much as I like. Okay? Then I go to Q1, and therefore I accept that input. 1, 0. Yeah?
Would the machine favor the Q2 then Q1 because it accepts closer because it was choosing?
The machine's not worried about efficiency here. In this class, we're not worried about efficiency. As long as we can do it, we're fine. So you're right that it's fewer transitions, but as long as there's some way for me to accept, I will take one of those choices. Okay? So clearly, there's no way to build any non-deterministic device in the world ever. So this is just a purely theoretical model that'll help us solve the problem of concatenation. Okay? There was another question over here. No other questions? Okay. So what did we do once we defined a DFA? What was the thing we defined next? We formally defined a DFA, but what else did we formally define? It starts with com and ends with putation. A computation, right. But immediately look at this. How many possible accepting computations did this string 1, 0 have? 2. How many could a DFA have? 1. So we're going to need to worry about that there may be more than one accepting computation, or even computation in general, for an NFA. All right, so a computation of an NFA, I'm going to call it M, with the 5 pieces, just like before, if I don't run out of room. On input W equal, on input W in sigma star. Well, before, the way we defined DFA computations was we said that each of the characters of this string W is a single character, and then we looked at a computation as a sequence of states where we read one character every single time. And since we would know the length of the string W, we know how many states that there will be. But what's the difference here? I may have empty strings scattered throughout. I may execute some epsilon transitions along the way. So, but how did I accept before? If I look back here, if I, for some whatever reason, couldn't progress beyond when I was in Q2 and I just saw 1, if I couldn't progress beyond that, would I ever accept the string? No. So we need to have a way to incorporate seeing epsilon transitions, but we also have to read the entire string. Okay? So on input W, where W equals, instead of W1 through Wn, I'm going to have Y1 through Ym with each Yi not only in sigma, but it could also be epsilon as well. So the only difference here is that I'm allowing for epsilons to be placed in the middle of the string. But I say that W is equal to this string, so that must mean I must read the entire string here in order to say that it's a computation, just like with DFAs. Same thing with NFAs. All right. Well, when I'm doing either a single character transition or an epsilon transition, I'm only doing one transition each time. So if I have M either characters or epsilons here, how many states will I see? Well, how many transitions are here? M transitions, so how many states will I see? M plus 1. So all this is an M plus 1 tuple of states, not tuple, M plus, let's do it this way, is a sequence of M plus 1 states. R0, R1, same thing as before, Rm. So I really do have M plus 1 states here. Okay, but then we can't just have any sequence of M plus 1 states. We gotta make sure that it's a valid computation. So what's an easy stipulation that I know about this sequence? What is R0? It better be the start state. So exactly the same as with DFAs. And then for the second one, let's remember what we wrote, and it's not going to work here. So what we wrote before was, what we had was Ri equals, no, we had Ri plus 1 is delta of Ri with Wi plus 1. Why will that not work here? It's not deterministic, but more importantly, what does the transition function output? So we'll go back. It outputs a what? It outputs a element of the power set of Q, which is a what? Set. Is a state a set? No. So this is clearly not going to work. But how do I know that Ri plus 1 is valid from Ri? So Ri, comma, Wi plus 1, that gives me a set of valid transitions that I can do. How do I know that Ri plus 1 is valid? I have a set of possible transitions that I could do. How do I know Ri plus 1 is a valid one to do? To go to? Yeah, it's a valid transition. Well, if this thing is a set, this thing, how do I know that Ri plus 1 can be achieved from there? It's in the set, right? So instead of being equal to a single state, it's going to be an element of the set of possible things that I could do. Okay? So I'm going to move this down over here. So I'm going to say here that instead of being equal, it's going to be in the set delta of Ri, Wi plus 1. For, now let's make sure we get the indices right. So I is going to be at least 0. I is going to be at least 0 and at strictly less than m. The indices are a little different than last time, but it's the exact same type statement. Okay, so just to recap, how do I achieve R1 from R0? I'm going to look at all the possible things I could do with R0, and R1's going to be one of them. Okay? Then once I go to R1, R2 is going to be one of the possible valid things I can do from R1, and then through the entire string. Okay? Yeah.
So it's going to be random. Like the machine is just going to pick one.
So I'm going to avoid that discussion. All we know is that it's going to make a decision that is, if there is a way for me to accept, it will make that choice.
So well, not random, it's more of the best possible decision to make?
It'll make a decision that'll get me to eventually accept, if there is a way.
Okay.
So it's like saying, I know how to get to this final state. I'm going to pick the way along that way. It's like I can predict in the future.
Okay.
Yeah.
Kind of like a branch prediction, kind of.
It's not really like branch prediction. It's saying that it's like if you somehow knew exactly what transitions to eventually do, it will do those. Yeah.
Going off of what you said about R1 being one of the states you can reach from 0, and then R2 being one of the states you can reach from R1,
Mhm.
that is assuming that it's guaranteed. So writing Ri plus 1 exists in the transition function.
Yes.
Is
Yes.
assuming that there is a transition
Mhm.
that can take you to each state.
Exactly.
But what if there is
What
no
if-
transition
what
to
if
take you to that state?
Great question. What if there is no transition to do? Then can I get to the end of the string if I'm stuck in the middle? No transition I can do. So if I'm stuck in the middle and I can't reach the end of the string, is it a valid computation? No. So it's not a valid computation. Yeah. Speak up, I can't hear. Not for NFAs. For DFAs, yes. NFAs, there may be 0, and we'll see, could be 1, could be infinite, actually. Yeah. I actually made a mistake here. Can anyone find the mistake? And I'll go up that far. I'll give you a hint. It's with the second stipulation on Ri plus 1. Y of I plus 1. Correct. So that's supposed to be Y of I plus 1. because I may very well execute epsilon transitions along the way. Okay? But any other questions about NFAs? The formal definition of NFAs and computation. Okay, so then we define just like before, the language of an NFA M is the set of all strings for which M has an accepting computation. And just like before, that means that Rn is an F. Not N. R sub M is an F. So accepting computation, exactly the same as with DFAs. The state that you land in at the very end, that's a final state. And we say the language of this machine M, this NFA, is the set of all strings for which there is at least one accepting computation. Okay? Whereas with DFAs, there can be at most one computation. There could be 0, but there can't be any more than 1. Here, I could have 0 accepting computations, 1, 2, and actually it could be infinitely many. And I'll give you a short example for that. So here's an example. So it's actually a very, very small example. Let's give it a name. Okay. Does this NFA accept the input 0? Yes. How do you know? Yeah, there is a direct transition there. So there's at least one computation that is accepting for this NFA. But let me ask you a question. How many computations are there on 0? Infinite. How do you know? I can take that epsilon transition as many times as I like. So the answer is infinite. And actually, this is accepting because I take that epsilon self loop as many times as I like, then take 0 over, and then now I accept. What about same thing, but the input 0, 0? There's 0. How do you know? There's absolutely no way for me to read the whole input. Do I need to read the whole input for it to be a computation? Yes. So the answer is 0. This is quite different than what we've seen with DFAs, where we had exactly one computation, whereas here we could have 0, 1, or even infinitely many, or any number in between. Okay? So the world's a little different here. All right. So what were we trying to do? What we were trying to do is generalize the model of NFAs, model of DFAs to get NFAs, to try to solve the problem of what? Concatenation, proving closure under concatenation for regular languages. Could I do concatenation for NFAs here? I have not proven that NFAs recognize regular languages yet, but can I do it for the set of languages accepted by NFAs? So let's start off with an easier example. So let's do union first. We'll actually do all 3 of the regular operations. So can I, given NFAs M1 and M2 produce an NFA for L of M1 union L of M2. So I want an NFA that has the language, the original guy's language, union the other one's language. Well, let's see. Do I know the structure of these two NFAs? Other than the fact that they're NFAs? No, I know nothing about them. They may have 0 final states. They may have no epsilon transitions. I have no idea. But I know that they exist because I just said that they did. So let's suppose that they have these black boxes, literally black boxes. Well, what else do I know? I know that they have some start state for each of them. So let's say that that's the start state of the first machine for M1. And let's say that this is the one for M2. And maybe this one has 2 final states. Maybe this one has 3. I don't know in general, but I know that they have a start state. And that's actually going to be the only thing that matters here. Could I produce an NFA using these two NFAs that has the language that is the union of both of them? Yeah, how do I do it? Oh, could I make a new start state and epsilon transition my way to both of the original start states? Let's see what happens if we tried that. So be prepared, different color. So I'm going to have, I'm going to have a transition that is epsilon transition on both of them. Well, let's be sure. Suppose that whatever string I have is in the language of M1. Do I have a computation, an accepting computation in this modified machine? Yeah, so what I do is I choose, because the NFA could choose, the top epsilon transition, and then do the original computation in M1, because I know that there is one, because it's in L of M1. Same thing if the string is in L of M2. If it's in both, then it's going to make one of the choices. I don't know which, but it's going to make one of them. And since it's in both, I know it'll accept it either way we go. So this NFA has the language L of M1 union L of M2. A lot easier for NFAs than DFAs, right? Cool. Let's see how NFAs could even help us with concatenation, the problem that was so hard for DFAs. Let's try it for NFAs. So concatenation. So let's say that we have the same black box for M1 and has, let's say, 2 final states. And let's say M2's here. Let's say it has 3 final states like before. And here's its start state. Could I get an NFA using these two that recognizes the concatenation of the original 2 languages? Yeah, so do you guys have an idea of how to do that? That's almost right. I don't need that extra start state. Yeah, I don't need that extra start state, but that's a great idea. Let's see what happens. So what I'm going to do is I'm going to epsilon transition my way from only the final states in the original M1 machine to the start state of the second machine. Is that all I need to do? You can tell by my tone that it isn't. Yeah, I need to make these 2 guys non-final as well. Why? Because I only want to accept when I've read something in M1's language, then M2's language, and concatenate it together. So I only should accept in the part of M2. Okay? Because remember, non-determinism says if there is some way for me to accept, I will accept. So if I left those two states final, then I could just stay in M1 and never do anything else. So I would get the language of M1, not necessarily the concatenation. But why does this work? Well, let's see. If I have a computation in M1 and a computation in M2, could I put those two computations together? Yeah. Would that get me the concatenation of the two parts, though? Yeah. So what would happen? I do the computation in M1. That gives me the string that I want in M1. Then I epsilon my way over because that's the only way I'll ever possibly accept the string. So epsilon over, that doesn't change the string that I've read so far because epsilon transitions don't read. Then I do whatever I need to do in M2. And that'll consume more of the input, and therefore I would accept if it's in the concatenation. So I get exactly the concatenation of these two languages. Yeah. So I can't hear you. What notation? That notation is just, it could extend to any NFA. So I'm just saying for every one of the original final states of M1, make it non-final and add an epsilon transition to the start state of, the original start state of M2. I'm just saying if it happened to have two, this is what you do, but it's easily extendable. I could make this formal, but it would take way too long to do all the details. Any other questions? All right, so let's quickly do the last one, which is star. And this just says, if I have an NFA for some language L, could I make an NFA for L star? Which means going through the language, picking some string out, and concatenating it over and over and over and over. You have a question? Okay. So let's suppose that I have a black box for, so now we have only one machine to work with, and let's say it has two final states. So can I get an NFA for the star of this? So first off, what string is always in the star of any language? Epsilon. Well, does that start state right there have to be an accepting state? Well, when I make one for the star, it will be, but I don't know that yet. So I can't work with this start state because if I make it final, then I may mess up a computation within M1, which would make me accept more things than I previously would have. So I cannot make that state final in general. So what do I do instead? Make a new start state that is final. So again, a different color. So make a new start state that is final. And so how am I going to connect that new final start state to the original machine? Epsilon transition my way in. Why? Because I want to start in the original machine as if I haven't read anything. And this gives me a way to do so. I could take that epsilon transition, I don't have to, but it gives me a way to start as if I haven't read anything. But this doesn't give us star yet. So what do I need instead? Not a self loop. I need a way to go back through the machine as many times as I like. So I need to go from what to what? Final states to where? Which start state, the original or the new one? The new one, good. It actually doesn't matter, but I want to modify the original machine as little as possible. And so here, there's no internal transitions that are added, only external ones. So let's just be sure that this is correct. If I have a computation in M1 for each of the pieces that I'm going to concatenate together, do I have a computation here? Well, I start in the start state, this new one, epsilon my way in, do the first piece, which means I end up in one of those final states, epsilon my way back out, then epsilon to the start state again, do the second piece, come out and do the third piece, fourth piece, and all the pieces that I need. So this is a valid construction for star. Any questions on this? Yeah. Yeah, I could go back to the original start state, but I want to modify the original machine as little as possible. It is completely valid, but there's absolutely nothing wrong with it, but I want to modify the original machine as little as possible. I do need a new start state, though. Yeah. Yeah.
I have one question.
Yeah.
If you're presented with the choice of an empty set, you have to proceed on that. Is that correct?
No, I don't have to execute an epsilon transition. All right.